Hello everyone, my name is Heydari, and in this video I'm going to present a recent research named Don't Look Back, which is an online music beat tracking method using RNN and enhanced particle filtering, which is conducted at Airlab, University of Rochester, under supervision of Professor Duan. So let's get started. So probably the first question that comes to mind is that what is the necessity of having a good music beat tracker? The response to this question is pretty simple. Music beat is the main tool for music time analysis. And also music beat tracking has a lot of applications on like other music related research and tasks. For example, in music generation, in music analysis and music processing, music beat tracking has applications, and you can see some examples for each. So let's start with the related works. We divided the related works to two categories. The category number one is the classical methods, and the category number two is deep neural net-based methods. So classical methods utilize onset string signal as the main feature, and then they extract the beat positions based on some probabilistic inference models. So here you can see three examples of classical methods. All are using onset string signals. So classical methods also have some advantages as follows. They are usually faster and also unsupervised. On the other hand, they suffer from some drawbacks. They are prone to noise. The onset string signal is not very informative feature. And also they are limited to music genre. And also the performance of this classical methods is not very promising. On the other hand, we have deep neural net-based methods. The main difference in here is that these methods use beat activation that is coming from neural net structures, so that they utilize some neural net structure like recurrent neural nets or convolutional neural nets to obtain the beat activation. And based off the beat activations, they again apply some probabilistic models to infer beat positions. And here you can see RNN plus peak picking or autocorrelation function or dynamic Bayesian network or CNN plus dynamic programming. So these methods also have their own advantages. They usually have better performance and they are more generic. And also they usually are more robust to noise. The main disadvantage of this deep neural net-based methods is that they are supervised, which means that they require a lot of labeled data, training hardware, and training time. There is an alert in here though. Most of the mentioned methods aren't fundamentally online, but applying a moving window trick to an offline method to make them work in online fashion. So what does it mean? Imagine we have a music signal and we have an offline beat tracking model. So we can easily apply that offline model on a chunk of this signal. And then we can extract the beats within this time. And based on these patterns, we can expect or we can estimate what will happen next. And we can do the same thing in the next coming time. And again, expect what will happen next. On the right-hand side, we have an animation to show how moving window trick works. So there is a big disadvantage in here, and it is the initialization window requirement. So as you see, the green bars are started after a couple of seconds because we need some time to form the first window and apply the offline method on the first window. And based off that, we can estimate the upcoming beat positions. The other disadvantage of moving window trick is that they suffer from discontinuity and potentially computational overload. So here we'll start presenting our model, which is fully online and it doesn't require initialization window or it doesn't require moving window trick. So let's get started. So as you see, we have the pre-processing unit, and then we feed the features, spectral feature to unidirectional neural net, and it gives us the activation function, which tells us how likely our current frame is a beat frame. And then we feed it to a particle filtering inference model, and it gives us the beat positions. So let's just go to the particle filtering part. So here is our state space transition model and observation model. Imagine we have one state space that is a 2D discrete state space. Each like dot, regardless of the color, yellow, gray, is one state. And we have one dimension that is the frame phase within the beat interval, and also the other dimension that is a tempo. So here we have different pace, different speed. So we have two scenarios. At the top row, we have only two frames that construct one beat interval. However, the bottom one requires 11 frames. So what this gives us? It tells that we need to pass like 11 frames to get to a new beat position. So if, for example, each frame is like 10 milliseconds, we require 110 to go from one beat to the next beat. And also we have our observation model for beat and non-beat. So the yellow dots are beat states, and we give them the weight that is coming from the neural net. This is actually the activation of the current frame K. And we also have non-beat states, and we give them very small probability, like a constant number, like 0.03. So we also have a transition model. So for non-beats, we just don't let the particles jump up and down. In other words, we don't let them change their tempo state. They only, in each frame, they just can jump to the adjacent frame. But at the end, when they are going to the beat state, they are allowed to sample based on this function. So they are now allowed to go to different tempos. This is important because this allows the system to track the tempo. And when we have like tempo fluctuation or tempo changes, also system can successfully track the beats. So how our algorithm works. We have initialization section that just distributes the particles uniformly in our state space. And then we update the state locations based on the transition probability. And then based on the new positions, we give them the weights that are coming from the LSTM activation functions and the gamma, the very small number, if they are non-beat. And then we sample based on their weight. And then based on the median of the clutter, we can say where is the position now. So here is an example. First, at the plot A, we distribute the particles randomly, and then they start to move forward. And when a high probability of beat occurs, then the particles within the beat interval get a high weight and the rest get discarded. And after a bunch of like iterations, they converge to the actual position. And in here also the vertical line, the blue line, is the median of this clutter and gives us the position of the current frame. All right, this is a video example of what actually happens there. So first, we distribute our particles randomly on our state space, and then they start moving forward based on the transition probabilities. And then by raising the first strong beat probability at the beat position, some particles that are in that area get more weight, and then they move. As you see, the highers are faster because they have higher tempo. And the same scenario happens again. The next strong beat probability happens, and again more things get discarded. And as you see,
bring my granulated sugar mama, sugar mama, ease my misery.
as you see, it converges to like this area. So in here, there is one important thing. Why these are not all in the same line of tempo? Because we want to investigate tempo fluctuations. We want to say what maybe in some scenarios tempo goes high and goes low. In this scenario, makes us able to investigate those scenarios. And if we have tempo fluctuations, this can easily just adopt itself with a new tempo. So let's go to the evaluation metric that we use. Evaluation metric for beat tracking is usually F measure, and we follow the same rule. So we have ground truths, we have a tolerance window of 70 milliseconds from each side of the ground truths. And if the detected beat is within this window as the red dot, we say we correctly detected the beat. And if it is not within this, like the green dot, then we say it was incorrect. And also this is our ultimate results. We have two F measure columns, one for 5 seconds skip and one without 5 seconds. Usually they report the results based on 5 seconds of song skipped from the beginning because it is like kind of true balance and stuff. So that's why we have like two columns in here. And as you see, the or don't look back system outperforms in both scenarios. The other important thing in here is that our model doesn't require initialization time. So the other online beat tracking models, the three ones, as you see, they require some initialization time, but ours immediately responses. And also we have two offline models in here that we brought. The reason is that we wanted to just compare how offline and online methods differ in terms of the performance. So since offline models have access to future and also they can get back and correct their previous detected beat positions, that's why they are usually better in terms of performance, but still, as you see, your model is comparable with this. Get the speed characteristic of our model. So we utilize 1000 particles. So it is faster than real time. Speed to number of particle ratio is almost linear. By decreasing the number of particles, the system gets even faster. So this plot shows the F measure of different setups, different particle numbers. The larger number of particles, the more accurate results. So in here, as you see, with very small number of particles, as small as like 300, still we have the better results than state of the art. And here, these plots are with and without the skip. Our model has its own pros and cons. So the pros are as follows. It is significantly more accurate than the previous methods, as we saw in the evaluation table. And also it doesn't require initialization window, which means that it delivers immediate response. And it is robust against greedy filtering, so that with a small number of filters, it still works good. And also it is a general approach, which means that it doesn't require the probabilities, the likelihood or posterior follow specific distributions like Gaussian, like in Kalman filtering we have that scenario. Since it is sampling-based method, it doesn't require this type of conditions. And also it is robust against tempo fluctuations. So as we saw in the video, since we investigate higher and lower tempi, it is able to follow the tempo fluctuations and tempo changes. The main disadvantage of our model is that its speed is lower than the non-sampling based models, but it is still faster than the real time. All right, thank you so much for watching this video. I hope you enjoyed this and you found the content interesting.